Okay, the Hangout is now live. We are honored tonight to have Dr. Renee Hlozek. She is she's currently a postdoc at Princeton University. Her background is she's got a degree in physics and mathematics from University in Cape Town, South Africa. She has gotten her PhD as a Rhodes Scholar from the University of Oxford in the UK, and like I said, is currently a theoretical astrophysics postdoc for research scientist at Princeton University. So we're very glad to have her here this evening. Her seminar series is titled Current Challenges in Cosmic Microwave Background Cosmology. A reminder, this seminar series is supported by a grant from the University of Central Arkansas Foundation, and we are happy to have you here. So take it away.
Thank you so much. It's really wonderful to meet you all on the internet, because that's the way things work these days. I'm really honored to give the talk, so I really appreciate the invitation. What I'm going to do is take you away from my face and to my slides. So here we go. Okay. So I'm going to start the talk, obviously, with a plug for one of the videos that I sent round. The reason why I advertise this is a couple of reasons. First of all, it's always fun to watch a video about the death of the universe, obviously. But I think it's something that is simple enough and interesting enough that you should all get your, mom, dad, sister, brother, or whatever to watch and have a conversation around it, because the universe is incredibly simple. And I hope I will outline some of what my work does to try and understand that in the next few slides. So it's always good to really, oh, can you still see me? Sorry.
Infinite regression. There it is.
Infinite regression, here we are. Okay. So I think it's always good to kind of set the stage as to where we are and how things work on the biggest picture. And so I'm going to give us a kind of 2-second introduction to how the universe behaved at really early times. So we know that the universe is made up of various components. We have matter, we have radiation, and these components change differently and evolve differently with cosmic time or with redshift. So on the x-axis of this plot, we have Z, or Z, as you all say, and that's giving us the redshift evolution. And the y-axis is showing the density. And the point of this plot is to say, look, the densities of the universe change with time. So we started in a universe that was very hot and dense and was mainly dominated by radiation. Then, as the universe cooled down, initially it was made basically of electrons and protons that were separate, and they were interacting in this cosmic soup. And the electrons in the cosmic soup were interacting with photons around. There were lots of photons around, and they're interacting via Thomson scattering. But it takes a little while for the universe to cool down, and once the universe had cooled down enough, the electrons and protons that were once just hanging around as free agents can really combine to form neutral atoms. And that's what we call decoupling. So initially the universe was dominated by the radiation. It then moves into a phase of matter domination, and then after another period of time, we have what we call decoupling, which is where the universe goes from being opaque to being transparent. And this is really important because it will frame what happens in the rest of cosmology and how we understand this time. So what do we do? Well, what we actually measure, we're trying to understand what the physics was like at shortly after the Big Bang, so around 380,000 years after the Big Bang. And the way we do that is we measure actually the temperature of this cosmic microwave background radiation. So as I said on the last slide, you had electrons interacting with photons through Thomson scattering, but once the electrons and protons are cold enough so that they can stably form neutral atoms, the radiation that was bouncing around can now propagate towards us. And this is what we call the cosmic microwave background radiation. It comes from the surface that we call the surface of last scattering, because that's the last time the scattering happened between electrons and photons. And what we're interested in is measuring the temperature of this radiation as a function of position on the sky. So the top equation is actually the kind of difference in temperature from one point to another. And what we do is we expand it in a basis. So we do a Fourier expansion, but we do an expansion on the sphere. Okay? And the coefficients of that spherical harmonic decomposition are what we call the CLs. So when you see CL, that's the magnitude of this expansion as a function of size. A way you can kind of think of this expansion is, if I just look in the room now, I can't see you, but earlier I saw you, and if I want to know, well, how is the density, what is the power spectrum or the distribution of density in the room? Most of the density in that room is on human-sized chunks, right? There's a table, there's some chairs, and there are lots of human-sized chunks. And this expansion is a way of saying that, like, how many spots on the surface of the sky are very hot or very cold. What is the kind of distribution? And so this tells us a lot about the early universe. So we have a pretty good model for how this behaves, and we have a lot of good codes that we can actually do to solve the equations in the early universe and generate maps like this. And in fact, what we typically do is we go from maps on the sphere, like this two-dimensional representation, to a one-dimensional power spectrum. So this is really saying, as a function of angular scale, so we have large scales on the left-hand side of the graph and small scales on the right-hand side, and we want to know what are the temperature fluctuations as a function of this angular scale in the sky. So what is the temperature fluctuations of the biggest blobs or the smallest blobs? And this is important because it tells us something about what the densities were like in the early universe. Okay, so what we're going to do is we're going to measure on maps of the sky, measure this power spectrum. Once we do that, oh, what I forgot to mention is that in the graph that you see here, the blue points are data points measured from the Planck satellite, and the red curve is a theoretical model. And what you'll notice is that in most places, the theoretical model fits the data incredibly well. And that's because we have a theory for how we predict this radiation to look like based on various components, the amount of matter, the amount of baryons, the amount of dark energy in the universe, and this predicts the spectrum pretty well. So what are the components of the universe? The thing that makes me the most amazed and really surprised about the universe is how simple it is. So most of the physics that we need is really controlled by 3 different groups, and in total just about 6 numbers. So there's a little plug. There's a really great popular science book by Martin Rees called Just 6 Numbers, and it talks exactly about this thing. Okay, so in the blue box we have the densities of the universe. So this is how much of the energy density of the whole universe is made up of various components. And we have baryon density, so that's omega ph squared, matter density, cold dark matter density, which is omega ch squared, and omega lambda, the dark energy density. In the orange box, we have parameters that describe what the density fluctuations of the universe were as laid out. And so the simplest thing we can do as physicists is to say, let's parameterize the density of the early universe as a power law. And that power law has some amplitude and some index. And so we say, as a function of scale, the density is distributed like a power law with a certain amplitude and an index. So that amplitude is delta r squared, or AS as we call it, and the spectral index is NS. Then the parameter at the bottom is called tau, and that is basically the optical depth, and is telling us something about how the universe went from being opaque sometime after the electrons and protons combine and form these neutral atoms. A long time after that, stars start to form and the universe starts to reionize. And so this tau is telling us about that reionization physics. Okay, so we have 6 parameters. Now the point of my work really is that I'm taking these measurements to a new scale. So initially we made measurements using the Cosmic Background Explorer. That was in the early 90s, and that's COBE, which is the kind of pink and blue graph. And COBE was great. It allowed us to measure the temperature of the CMB, but it didn't do so well on measuring the fluctuations because we expect the primordial fluctuations of the CMB to vary on a scale of about 1 degree. But the resolution of COBE was about 7 degrees. So we really needed to wait for smaller scale experiments to measure the fluctuations with a lot of precision. And so WMAP partly did that, And so you can see that the resolution of WMAP was 0.3 degrees, and Planck has taken that one step further, increasing the resolution even more. Now, the point about ACT, which is the experiment I'm going to talk a little bit about today, is that it increases this resolution even further. And that means that we can not only resolve the fluctuations of the primordial underlying cosmic microwave background, but we also measure light from stuff between us and the CMB, from dusty galaxies that are emitting in the radio wavelengths, from clusters of galaxies in their hot gas. And so we need to understand not only the primordial physics, but also the astrophysics in the way. So I just wanted to show you another animation of how we go from measuring fluctuations on the sky to a power spectrum. So this was made by BICEP for Planck, and I'm just going to play the video for you. So it should highlight on the graph. So you see a little yellow bit on the graph, and then it's highlighting the map that's used. Although I don't know if this is playing correctly. Here we go. And this is going to show you what the fluctuations on the sky look like in terms of the power spectrum. And it gives us basically a nice dictionary between 2 dimensions, maps, and 1-dimensional power spectrum. So on the larger scales, you see the red larger scales. Those are what the fluctuations would look like. As we move to slightly smaller angular size, so remember the angular size decreases as you go towards the right, you see that the fluctuations are on a smaller scale, which is kind of cool. And we can continue to move up, linking our 2-dimensional representation with the power spectrum in 1D. And so really what we see when we take any map from data is we see a combination of those, all of those scales at the same time. And what we do to measure this power spectrum is we then can decompose them together. So when you look at a map of Planck, you're really seeing all the fluctuations on all scales, and that's exactly what we measure. Okay. So my experiment, the Atacama Cosmology Telescope, is a collaboration of many different universities, and I've been lucky to be at a couple of them. And so we measure this light from the deserts of northern Chile. So we're about 17,000 feet above sea level, and the site was chosen because it's very dry. So we have very little water vapor in a year. So if you look on a good day, that's of course what you see when you look in the sky. No, it isn't. We take a long time to make those maps. But ACT is a 6-meter off-axis Gregorian primary mirror, and you can see in the kind of ground shield, it's sitting inside the ground shield, and it had a 1 arc-minute resolution. And originally we designed it to be measure this light from the cosmic sky at 3 different frequency channels, and that's important because we were interested in some astrophysics that comes from the Sunyaev-Zeldovich effect. And so we focus on 148, 218, and 227 gigahertz measurements. I'm going to talk about, we operated from 2007 to 2010. I'm going to talk about mainly work done at 2 frequencies, the 148 and the 220 gigahertz, and we observed both in the south and on the equator, and that's kind of important because it allows us to do different things. So I thought it's useful to, when you see maps like this, to really know how they get made, because then you kind of understand the point of the ACT data. And so this is a strip, one of our strips, and we show how we make a power spectrum. So we split out each bit of data, we split into 4 subsets. So how it actually works is the telescope scans the sky and makes measurements as a function of time. So frequency is a function of time, and we can break those measurements up into chunks of, say, 15 minutes long, and then combine them and split them up into 4 different groups and combine them to form maps of the same patch of sky, but made with different sets of data. And that's really important because we can then use those to make a power spectrum. But what we're not doing, we're not cross-correlating in space each of the little blocks with each other. We're actually really saying let's split our data up in the time domain and make spectra that way. Okay. So what do we see? It's important to relate maps made by different experiments. And so just for interest's sake, I've shown, well, I'm getting a little bit of feedback. Is everything okay?
Yep, we're good.
Awesome. Okay. So we relate maps taken with an experiment like Planck to maps taken with ACT. And this is kind of cool. So the top map is taken with Planck, and the bottom map is taken with ACT. Now you'll notice a few things. First of all, the very large-scale structure, so the like big dark bits, coincide between the two experiments, which is kind of neat. They were taken years apart with different experiments in different places, and we're seeing the same underlying sky, which is reassuring because we think the universe should be the same, no matter who looks at it, right? But one thing that you'll notice is the resolution is better in the map on the bottom. So ACT has a better resolution than Planck. And you'll notice different things, like we can see bright white spots, which are coming from radio galaxies, and we can also see dark kind of pinpricks, which are coming from clusters. So that's always reassuring. So what happens when we move from a map into this kind of two-dimensional power spectrum? So here I've shown the power spectrum. Now I'm going to have multipole on the bottom. So multipole is like the opposite of angular scale. So large multipoles mean small angular scales. And the y-axis is the power spectrum. And this is exactly what we showed before. It's a slightly different representation. I've just plotted it on a logarithmic scale. So that's why it looks a little bit weird. But the reason why I show it is I'm also showing you components that are not the primordial CMB that are adding to this power on small scales. So you'll notice on the left-hand side of the graph, all the graphs line up, and that's because they're all coming, all the radiation at different frequencies is coming from the CMB, and the CMB doesn't change with frequency. It's just sending out the same information. But as we go to smaller scales, suddenly the emission from galaxies and radio sources and clusters is increasing, and that's why you see very different graphs on the right-hand side. The 220 contains the most information from dusty galaxies. That's why it's very bright. Okay, so we have these beautiful spectra. We spend a lot of time figuring out how to make them and make them authentic. So what do we do with ACT data? How can we use the data that we have to constrain cosmology? Now, I mentioned before that we have these 6 parameters, the 3 densities, the 2 parameters that control the power spectrum of fluctuations, and then one that talks to us about the reionization physics. And the truth is, just with WMAP data, we constrained those 6 parameters pretty well. And so now we ask ourselves, well, when we have all this extra information on the very smallest scales, what can we say about different models of the universe that are a little bit different from the standard picture, but that are interesting? Can we constrain how different the universe is than the kind of simple basic model? So we call the basic model the kind of lambda CDM cosmology because it has lambda in it and it has cold dark matter. But now we want to say, can we constrain deviations from this model? Can we put limits onto how weird the universe can be? And one of the ways we do that is we say, what if there was some extra relativistic energy density at the CMB? So you can think about, what if there was another neutrino? Or what if we had some kind of extra radiation early on? How would this change the physics? Well, one of the ways that we discussed in the beginning is that the universe starts off radiation dominated, and then the matter content of the universe kind of takes over. And if we add more radiation-like substances in the early universe, what happens is we make this transition happen later in time. And that's one of the ways we can constrain how much of this extra radiation there could be in the early universe. So we call the parameter ineffective, which just says it's a kind of code word for saying, is there extra relativistic stuff? We don't necessarily know where it's coming from, but can we constrain how much there would be? Now, if we have a standard model with 3 neutrinos, then we expect ineffective to be close to 3. It's a little bit different from 3 because of decoupling in the early universe, but it's close to 3. Can we detect the difference between 3 and this parameter? So you can see in the brown contours, so these contours are 2-dimensional marginalized likelihood contours. So what I do is I perform a Monte Carlo Markov chain analysis, and I say, here's the model that I have. I pick a bunch of different parameters within that model, and I run it through the data. And then I see, does that data fit, does the predicted model fit my data? And I do that a bunch of times using a Monte Carlo Markov chain, and I can compute a statistical contour in 2 dimensions in these 2 parameters. So I can say, this model is pretty likely. So anywhere within the orange circle means at one standard deviation or 1 sigma, I can't tell the theoretical model away from my data. It looks similar at 1 standard deviation. So anywhere within the dark colored region is very likely, and anywhere outside of the colored regions is unlikely. Now you can see the brown curves from WMAP. There were lots of regions that were pretty likely. We couldn't really tell the difference between a universe that had an H0 of 70 or a universe that had an H0 of 80, just with WMAP alone. And so one of the things that ACT did is it allowed us, because the data got better, to make this contour a lot smaller. So suddenly you can see that the orange contour is much smaller than the brown. And the same continued with Planck. You can see the kind of black lines show us that we have a much smaller allowed parameter space in this plane, N effective and H0. And you're going to see these kind of contours a lot. Another way that we can make our simple model a little bit more complicated is we can say, well, we know we have constraints between on the scalar spectral index, so that's NS, which describes the power spectrum scale. But now what if we say maybe there is a little bit of gravitational waves? This has become kind of very hot recently, but even as far back as 2013, we were saying, well, what if there's a little bit of energy from gravitational waves? Can we put a constraint on the amount of gravitational radiation is allowed given our data? And again, you see from the brown contours down to the blue, we're really increasing the precision on that. And then we go that one step further with Planck on the allowed range of NS and R. But now I want to get even a little bit crazier, and I say, rather than assuming that my initial fluctuation, so these are the very tiny fluctuations in the densities of the early universe, and I've been saying that we use typically a power spectrum with an amplitude and a slope. But what if I don't know that that's true? What if I think there might be some crazy, funky physics happening that's going to put a big feature in my power spectrum? How can I constrain that? Well, one of the things that you can do is you can say, I'm going to let my power spectrum be basically free, not assume that it follows a power law, and I'm just going to allow it to vary in bins. So in this paper, I gave the freedom of 20 bins over a range of scales, and I constrained each of those amplitudes separately. And what you can see if you compare the brown stars to the orange bands, which are from WMAP, is we do much better at constraining the power spectrum with more data on small scales, so large values of K. Previously, we weren't entirely sure what was happening out to K of 0.1, but now we can do a pretty good job at understanding that. But this allows you to do something else neat. What I'm really showing with this plot is I'm saying, using the CMB physics itself, tell me what the fluctuations were like in the early universe, in the density of the early universe. So we see fluctuations in temperature, but we've really estimated the fluctuations in the density at the early universe. If I know that, and I've also constrained my other parameters, like how much matter there is and how many baryons there are, I can compute what we call the growth function. And the growth function says, how does gravity change objects? How do they grow with time? And that's uniquely predicted by general relativity and these parameters. And so if we know what the parameters are, we can take these fluctuations and we can really grow them just under the simplest form to say, well, what will the fluctuations look like from the CMB? What do they look like if we kind of grow them to today? And so that's what we see in this plot here. So this is the kind of matter power spectrum plot that you might have seen from other experiments like the Sloan Digital Sky Survey. But what I've added to is I've added points, the brown stars, where I've estimated the power directly from the CMB. And this basically shows us, it's important to notice that I've put all these data points down from various experiments, but the black line hasn't actually been fitted to the data. That's just a prediction of what we think the power spectrum should look like in this lambda CDM cosmology. So we do a pretty good job of matching the data, even if I haven't actually fit the coefficients to the line directly. So we're able to look at the CMB and find out not only what were the fluctuations like in the early universe, but what would they look like today on the larger scales. Great. So this was an introduction to things you can do to try to take from your data to understand our universe. And one of the challenges going forward is looking at different models of the universe and how we understand them based on our data. I want to change gears a little bit now and talk about how we actually can make the data better and how we can challenge and test for the data. So this is based on work that I did. It's recently been published in Physical Review D, and was looking at, can we try and understand and reproduce some of the analysis of a different experiment using their data to try and see if we understand things. And so this was looking at Planck data, but one of the things that it's worth reminding ourselves of is that the universe using different experiments is pretty consistent. I showed you the plot earlier of the WMAP, so the ACT data on the corresponding Planck plot, and things are pretty consistent there. And you see the same thing with WMAP, which is shown here on the left, and Planck, which is shown on the right. These are maps made from very different experiments, and they show a pretty consistent picture about what the universe looks like, which is very reassuring. But a couple of years ago when the papers came out, we really wanted to understand this a bit better. So here are the maps made by Planck at a variety of frequencies, going from 30 gigahertz on the left to 857 gigahertz on the right. And you can see that while we expect the CMB to kind of stay roughly constant with frequency, we do notice that the maps look very different. And that's because all the other things, the astrophysics between us and the CMB, is changing. So our galaxies, for example, much brighter in dust. We have other sources that are showing up. We have synchrotron emission. And so these processes all have different wavelengths where they peak. And what I was interested in doing, this is a paper I did with David Spergel, who's on the left of the plot, and Raphael Flauger, who is on the right of the plot. We wanted to look at the Planck data and see if we can understand it and if we can reproduce some of the analysis. So this, again, is a power spectrum that you've seen before, but now it's of Planck data at their various frequencies. And you can see on the right-hand side of the plot, depending on your frequency, the data points go away from the curve, which is the primordial signal, and that's because of foregrounds. Okay, so we were looking at the papers, and one of the things you should all be doing when you read a paper is see if you agree with things, and if you don't, that's fine. You should probe and test and kind of figure out why. And we noticed something slightly strange when we were looking at the papers. So whenever you see the word CamSpec, that is, you can keep in your minds, that's the number that Planck found with their own analysis a couple of years ago. And what we noticed was that if you compare the green line in this plot to the black line, you see a shift. The best fit value is moved over to higher values of the scalar spectral index. And we were a bit confused because this is only with Planck data. The only difference is they removed one chunk of the data from their analysis. Particularly, they removed the data at 217 gigahertz. So we were a bit confused as to why there was such a big shift in the parameters. We also then looked at some of the tests that they presented. So these three panels that I'm showing you here are what we call null tests. And a simple way to understand that is I break my data into chunks. Say I use all the data from 1 year of my survey and all the data from another, and I compute the difference between the two maps. I literally take one sky and I subtract it from another sky. And then I compute the power spectrum of that. Now, because we think that the CMB shouldn't change from year to year, if I get a significant difference, it's something to do with my analysis. And so it's a way of, it's a null test, which is what we call them, to try and see if there's any issue in your analysis. And what we noticed with the 217 gigahertz data is there seemed to be some issues. The data points seemed to deviate from the curve on a few different scales, and we were interested in why that was the case. Finally, one of the things we noticed was that Planck has a foreground model that's similar to the one I showed you with ACT, it has dusty galaxies, and it has information from clusters. And the top panel that you see in this graph is the Planck data minus the best fitting predicted cosmological CMB model. And so you just see something that looks like foregrounds, which is fine. The individual orange, blue, purple, and green kind of match up and add to the total foreground model, which is shown in red. But the bottom panel is when you take those blue data points and you subtract the red line. So this is whatever's left over after you've taken your best cosmology out of the picture and you've taken your best foreground model out of the picture. And we saw that there was this weird oscillatory structure which we didn't understand. And we wanted to understand that a bit better. So this led us to think we'd actually like to reproduce the Planck analysis. Now, we could only do that because the Planck team made their data available online. And so it was possible for us to go and take their maps and really do our own analysis. So I'm going to give you a super brief rundown of how that happens because it'll be relevant to understanding why it's important. So typically, the way, as I said, the way CMB maps are made, you take these chunks of data and you map them into a map at different frequencies. Now, how you combine those chunks of data depends on you and can vary. I talked to you about the ACT analysis, about how we split up the chunks into 4 different parts, kind of randomly, and then made 4 different maps. Now, the way Planck works is they have many detectors. Sitting at each frequency, they have many different detectors. And so you can either make a map using all the data from your 2 years and make 1 map per detector. You then have many different detector maps and you combine them to make a power spectrum. Instead, you can say, well, let me only use 1 year of data, but throw all the detectors together. So throw all the data from all the detectors together and make 1 map per year. Now that's important because the analysis that Planck did used these detector maps, but the maps that they released online were the season maps. So there were fewer maps that allowed us to do different things. Okay, so now you've made a map of the CMB. Before you take a power spectrum, you make a mask, and that removes all your galactic emission and emission from like galaxies that you know are there because you've seen them in other sources. The reason why I show this is it's because it's super important. We normally show maps of the CMB that have been cleaned of almost all the galaxy. But when we're actually doing cosmology, we mask out most of the galaxy, which is important to note. And so we decided to reproduce the Planck masks. Now you'll notice in the bottom left-hand graph, it's similar to the top, but there's this weird stripe. And that's going to prove to be quite important because when Planck made maps of the seasons, not all of the sky was observed in both seasons. So 1 part of the sky was only absorbed once. And so we can't use that if we're making a seasonal map because then you really have, you have 1 map which has no information in 1 part and you can't cross-correlate that with another map. So we have to mask that out. After you make a mask, you then compute your power spectrum. So you do a correlation, a 2-point correlation between 2 different maps, and you come up with a power spectrum, which is great, and that's what Planck did. So again, to put it kind of visually, they used these 3 maps for their cosmology. They used 100 gigahertz, 143, and 217, and then they used for masks, they used the 353 gigahertz maps. Now, what we decided to do was we know that if we look at these maps, we see some of the structure is repeated in all 3. So some of the dust that you see in 217 will also be there in 100 gigahertz, or some of the dust you see at higher frequencies we know is going to be there at lower frequencies. So we decided to clean the maps a little bit. And the way that you can come up with a clean map is you say, well, if I want a power spectrum that's clean, and I make it between 2 different maps, I say that I can take one of my maps and define a coefficient alpha, which is a constant just for 1 frequency. My clean map will be 1 minus alpha times that map A minus alpha times map B. And that basically is saying, I want you to remove all of the power that's common to both. So if I think there's dust in both at the same places, take that out and find the coefficient that takes that out the most cleanly by minimizing the kind of power spectrum on small scales. So we used the 3 maps in the middle for our analysis, but we also added the higher frequency maps, which we used to clean up the lower frequency maps, whereas Planck didn't use that information. So what happens? Well, on the left and right, I show the spectra before and after cleaning. So you see that on the left-hand side, as you go to higher frequencies, the data are really dominated by dust and other sources of emission that are not the primordial CMB. So the points literally rise up off the primordial CMB prediction, which is shown as the black solid line. But once I do the cleaning, I really can kind of zap those back down to the primordial cosmology because I've removed all the common dust emission from the two. So this is pretty neat, and I was really surprised when I saw this. Once we then took the power spectrum of these new power spectra and computed parameters just by running them through our normal chains, we found something quite interesting. So the top left graph is reproducing what I showed you from the Planck papers, which is that if you look at the blue lines and compare the blue solid line to the blue dashed line, you see this is what we saw before. If I remove the 217 gigahertz data, the Planck value shifts. But what happens with our cleaned spectra is shown in the black lines. And here you see the shifts are much smaller, and they don't really it doesn't really matter if you go from one frequency, if you throw away one frequency. What is important is that the black solid line is shifted from the blue solid line. So even though we use the same data, we just clean it a bit, we get very different cosmology out, which is kind of interesting. So if there was something wrong with the cleaning, you might say, well, why did Planck not do this cleaning themselves? Because it seems like there were some big shifts. And initially we were worried about that. We thought, well, maybe Planck should have done more cleaning. But it took us a lot of investigation, and in science this is awesome to do, to really hunt down the source of the error. And we realized it wasn't actually the cleaning that Planck was doing wrong. It was because we had different maps. So they had released these detector sets, and we had maps that were from the seasons. So I'm going to skip a couple of slides, but basically what we showed is that even if we didn't do any cleaning at all, if we used the maps that were released publicly, we found a lot of the shifts similar to when we did cleaning, and they were different from the results that Planck put out online. You can see this a little bit visually. So in these panels, I'm taking the spectra that I made using the uncleaned maps, publicly released maps, and I'm computing the difference between the spectra that were released publicly. And you'll see that there's a spread in all of them, but say at 217 gigahertz, there seems to be quite a lot of a discrepancy at small scales. And this is showing you that there really was something different in the data in the maps. Now, in a few days' time, we'll see new Planck papers. There have been a couple of Planck conferences where they've talked about this, and actually in the news analysis of the results this season, they are only using seasonal maps, which is the ones that we used, rather than the detectors. So hopefully some of these systematics that we saw will go away in the big release of the Planck data coming up shortly. But one of the reasons for bringing this up is I want to stress how important it is to really test for systematics in data and to really understand your data, whether it's your own or other people's data as it comes out. Okay, so I'm going to shift gear a little bit more, looking at the future. So we've had data in the temperature regime I've talked about results from ACT, and I've talked about results from Planck, but what's next is polarization. So rather than just measuring the temperature of this light, we know that light from the CMB will be a little bit polarized. And that level of polarization tells us something about the early universe. So we recently presented our results from the polarization instrument of the Atacama Cosmology Telescope. And you can see here we have various fields in the equator that we use to make our maps. Now, what do the data look like? Well, on the left-hand side, you see the typical temperature maps that you will have seen before. And if you zoom in, you can see these clusters and point sources. But interestingly, if you look at the Q and U, so these are the two Stokes parameters, two different types of polarization, we actually see very specific patterns that we expect from what we call E-mode polarization. E-mode polarization is related to interesting physics in the universe that isn't directly related to gravitational polarization, which is what the BICEP experiment recently was presenting results on. You can kind of see that we don't have B-modes in our data because if you look at the bottom right, which is the B-mode polarization, it looks the most kind of bland or noisy than the others. There's no real pattern to it. And that's one of the ways we can see even visually that there's not a lot of B-mode polarization in our maps. If we look at the power spectrum, now this is similar to the power spectrum you've seen before, but you'll see that the error bars are still large and we need a lot of work, but this is really the next generation of experiments and how we're going to improve going forward. And in B-modes you see kind of the same thing. There's not a lot of radiation, there's not a lot of power in the B-modes as such, and the error bars are still pretty big. Okay. So I'm going to skip a little bit of this and kind of highlight things going forward. Again, this is from the Planck release that happened a couple of weeks ago. The papers aren't yet out, but some of the visuals are out. And this, again, is a map now of polarization and temperature. So the background is actually the thermal emission from dust, and the kind of rippliness is the polarization signature. So this is coming from polarization of dust in the galaxy, but ideally we want to make really good maps like this of the cosmic polarization of the kind of gravitational signals. And at the moment it seems we're dominated by dust rather than a primordial signal. Where are we going next? Well, we know that dust is a problem for polarization and we really need to understand it. So one of the ways that ACT is going forward, and there are other experiments doing the same thing, is measuring this polarization, but now at a variety of frequencies. So you see the 5 bands that ACT is going to measure in 28, 41, 90, 150, and 230 gigahertz, and then we'll supplement with higher frequency Planck maps. That's important because all of the different foreground components, so dust, synchrotron emission, etc., has a different behavior with frequency. And so we really want to measure the polarization effect as much as we can by cleaning out a lot of the foregrounds. When we do that, we'll have a survey of 20,000 square degrees, so a very large scale, and it will overlap with data from many different surveys. So we'll really be able to pin down the polarization and combine with other experiments, which is very useful. And this will allow us to learn a lot about the universe in different ways, understanding how reionization happened in the early universe. So the plot that I'm showing here is kind of neat because we realized that using the polarization data, we can constrain what the cosmology is like. So these are the 6 parameters I told you about before. And that means we can actually predict what the temperature power spectrum is that we should see. But in future experiments, we're also going to make measurements of the temperature power spectrum. And so you can actually use the data and the prediction to measure interesting physics of properties of sources between us and the CMB. And most importantly, we use this to talk about the Sunyaev-Zeldovich effect. In a nutshell, what the SZ effect is imagine if there's a large galaxy cluster that's sitting between us and the CMB. What happens is a photon interacts with the galaxy cluster and it upscatters off the hot electron gas in the cluster. So it gains energy, and that means that its spectrum gets shifted to the right, to kind of higher energies. This means that if you look at a cluster at a variety of frequencies, it'll either look like a bigger cold spot, or it'll be invisible, or it'll look like a hot spot. And that's what you can see by this kind of solid line on the curve, is that there's a very specific frequency dependence. So clusters look different depending on what frequency we look at them in. What we can do is we can actually also see if the clusters are moving, because if they're moving because of the Doppler effect, they're going to add an additional boost to this light. And so we can actually measure that using the CMB. And future experiments from ACTPol will allow us to really detect this to very small scales, which is useful. So there's a lot of information here, but what I was hoping to instill in you is that CMB cosmology is going through a kind of revolution in the sense that we have data from different sources. We have experiments on the ground like ACTPol, experiments at the South Pole like SPT. We have measurements from Planck, which is in space and releases its data soon. And we also have other measurements on the ground that are making really interesting and detailed maps of the sky at different frequencies. This allows us really to probe new physics and to look for searches, look for substances such as different parameters or gravitational waves, using not only the temperature but also the polarization signature of the light. Finally, I sort of illustrated an analysis that we did to try and reproduce and understand data from the Planck satellite, which is really important if we're to understand the systematics of various experiments. And so putting all these things together allows us to build a really robust picture of the universe and what it contains, so that we can continue to move onwards in the journey of observational cosmology with a cosmic microwave background. So thanks.
Cool.
So I guess I'll go to screen view. It's crazy, all the things. There we go.
Okay, so a quick announcement to those watching online or on the YouTube stream. We're going to be taking questions for Dr. Hlozek here soon. And if you have a question on Twitter, just use the hashtag GHOSeminar. Otherwise, use the Q&A feature on Google Plus to be able to ask a question. Right now, I'm going to throw it open to questions here in the room. Do any of our students here have a question? Or I can ask my question.
It was a lot of information, so feel free to go back to the beginning.
Lucas, what you got?
Just something that I noticed right at the beginning. You have quite an interesting background. So you grew up in South Africa and then moved to, you got your doctorate at Oxford and now you're at Princeton. You could talk to us a little bit more about your graduate experience and got you into science and stuff like that.
Sure. Yeah. So I think, you know, I grew up in South Africa. I did my undergrad in my hometown, and I was really just interested in physics and astronomy. And I was lucky that I started doing astronomy and started meeting interesting people that were doing different things and different types of astronomy. South Africa has a pretty good history of astronomy because we have clear skies, which is really useful. And basically the fact is I met different people and I realized I want to try to study in different places and to experience things. And I got encouragement from friends to apply for the Rhodes Scholarship, which I almost didn't do because I thought whatever, they're not going to take me. And then I got in, which is fantastic. And then one of the things that I think is really important to remember, and it's easy if you, growing up in South Africa, it's easy to feel kind of isolated geographically because no one really paid attention to where I was from unless there was something bad in the news. At least I felt that, right? So
the American South and Arkansas in particular, we know exactly what you're talking about.
Right. Okay. So you get it. But one of the things I realized is that that didn't have to be the story because it took a while it took meeting different people to realize this, but doing science makes you a global citizen. It makes you a member of the international community. And so I suddenly realized that not only could I speak to people, I could Skype different people online, I could do what you guys are doing now, but also I could try and also apply further away and try different things, and I didn't have to worry that somehow there was something wrong with my education because no one had heard of the university that I went to, or I hadn't met that many people from outside of my hometown. I realized, oh, I'm just doing science, and people are doing good science with me. I'm intrigued by stuff, and I'm learning about people all over the world. And so that's something that I always encourage students to do. You know, write emails to people at universities that you don't know about. You know, heck, speak about coming. You know, think about applying to come and do a undergraduate summer program or whatever. It's great now, and I think this is a perfect example of this as we move forward into a different kind of generation where mobility isn't the most important thing that matters, is believing that you're part of a community that is international really changed the way that I looked at myself and looked at myself researching. I mean, I get to live in the US, which is kind of crazy, and I never thought I'd do that. I get to move around, but only because I decided that I wanted to be able to be a citizen of the world too. And moving around didn't come first. It was the other way around. That was much longer of an answer than you were asking for. Sorry.
Well, I've got a question about the polarization part of the cosmic microwave background. So I'm familiar. My training is more in acoustics, and so sound and vibration and that sort of thing. And so when I think about cosmic microwave background radiation, we're looking at the temperature fluctuations. That's the density fluctuations in the early universe. I think I'm remembering that right. And so that's sort of like, you know, sound waves or some sort of gravitational type waves that were causing density fluctuations. And so it's an idea about what the temperature picture is telling us about the early universe. But I don't know, and I don't know if the students have much experience with what is that polarization map telling? What's the fundamental physics that you guys are able to get out of that?
So that's actually a good question. A lot of the polarization is sensitive to the kind of electron density, because really, you know, you have this the fact that you have fluctuations means if you have an electromagnetic wave which naturally has two polarization states, and you interact with one of these dipoles, you're actually enhancing one of the polarization states because of this electromagnetic dipole. So the fact that the CMB has this dipole in it is why polarization happens. If it was just, if the CMB was completely uniform, if there were these fluctuations, the polarization kind of wouldn't get sourced. And so one of the things that polarization tells us is, if anything is, it tells us about what the electron density is and the electron velocity at the early times, but also if anything is strange is happening to space, in space-time, it can also change this polarization. So you can imagine you have this polarization state. I often think of, you know, like, I don't know how to do waves, electromagnetic waves that are going in two directions. It doesn't really work. If anything's changing space, you're basically compressing or expanding that oscillation. And so that's how, you know, gravitational waves will distort the polarization signal in a very specific way.
Okay. So now I can connect this back to something that the students take. So when you're junior, senior, you take E&M, right? Electricity, magnetism. And so one of the things that you talk about in, say, E&M 1 is the multiple expansion, right? And it's painful, right? But spherical harmonics, right? You're doing the multiple expansion, and you see the connection with what she just talked about, how if you have those charge distributions getting stretched or compressed or moved around, then that would show up.
Right. Right. In fact, it's funny, the spherical harmonic...
You were teaching stuff that's important for you when you go out here.
Yeah, it's amazing. So it's interesting, like spherical harmonics, it's something that's used so much because if we're trying to understand the pulsation of a star, we look at the same kind of modes, like what are the dominant modes of pulsation. We do it in the CMB. In fact, I was speaking to someone just today who was trying to make it relevant for students, and I'm going to find the blog post and maybe tweet it out at you later because I haven't seen it yet. But it's he did a kind of spherical harmonic decomposition of took a power spectrum of the Earth, of like height and depth, and came up with an expansion of the power spectrum of heights on the Earth, which I think is a great analogy, right? Because we're so bad at thinking of the relevance of like the cosmic microwave background. But yeah, spherical harmonic decomposition is amazing.
Yeah, that is cool. And it was also that ESA video was really informative when they took the map and they rotated it to where you could see sort of...
Right? Because that gives you the amplitude, right? If there was a lot more... So if the graph Hold on. I'm not going to try and draw in this air anymore because that was a super great job that I just did. So if you had, so this is the power spectrum.
Yep.
And so when it went to small scales, you saw that the fluctuations were tiny, but also the X and Y axis was little.
Right.
But now imagine if the power spectrum went like this. It would mean that on the smallest scales, the size, the angular size of the fluctuations would be the same, but the height of the peaks would be very different. So if we had the most power in those scales, you just see that they were very extreme, kind of like if you think of like white noise, right? If that level of noise is higher, that's what you'd see more of. So, oh, I have forgot a cool tip you can tell your friends, and this is almost not relevant anymore because I'm old enough that it's still relevant. But back in the land, the year before digital TV, we used to have TVs, right, that you tune, analog TVs. And sometimes you could tune not to a certain channel. You just have static.
Right.
When you do that, 2% of the light that you see on the screen is actually coming from the Big Bang.
Oh, really? Cool.
Yeah. So it's in the microwave. So if we could see in the microwave, there would be a lot of this radiation.
Cool. So we've got 2 questions on the Google Hangout, the in-app Q&A feature there. So if you go over and you click the Q&A button,
Oops.
I've selected one already. So Lawrence Norris is the guy behind the Black Physicists, National Society of Black Physicists Twitter account. And so he asked the question, I actually thought you were back at, looks like University of Cape Town. So you're not back there yet.
No. There is a woman called Renee at the University of Cape Town, but she's much cooler than me.
I don't know how that's possible.
Well, she's head of department, so
that's
cooler than me.
Something to strive for. So here we've got another one from Craig Landon. So I'll read out the question for those watching, and then you can answer it.
Sure.
Craig Landon's question is, how can your work with ACT cosmic microwave background be folded into the Planck work to further help to clean up the BICEP 2 work in order to tease out better understanding on the gravitational waves like the poster behind you?
So I think, the paper came out the last couple of days, kind of further refining the BICEP analysis with the cross-correlation with Planck. So in fact, Planck and BICEP really combined forces and said, let's do this kind of cross-correlation between our 2 maps. We have 2 maps on different scales. We filter them so that they're sort of on the same resolution, and then we cross-correlate them. And that allowed them to see how much of the signal was in both, given that the Planck map that they used was mainly dust. And that's what allowed them to see, okay, there's a lot of the signal is probably dust. But I think it's very useful or informative to think about what has been happening with this whole BICEP thing. The media has sometimes been, I think the media's done a good job of explaining different sides, but sometimes it's easy to think, oh, someone's right, someone's wrong all the time. And I think it's really important to see what happened. So in March 2014, the BICEP team released something, and they said, we have this 6 signal, we have this detection, and they thought maybe it's gravitational waves. And then myself and my colleagues on Twitter even were like, oh, there's this thing, what about this? Have you thought about this? I'm not sure I understand. And then people did various analyses to kind of check. And in a way, what we're seeing is the scientific method in public, which is not necessarily always done, but I think it's really useful. So the idea is someone releases something, and if I believe you, I want to be sure, and I want to check as much as I can. And you check, and I check, and we keep talking. And I think that that's actually worked really well. And to BICEP's credit, they combined with Planck. They want to test their analysis, and they're going to do more. They're going to make more observations of the sky. They're going to do more tests, and will further refine whatever we see. Now, there is a possibility that the gravitational waves could be around, but we now know that the amplitude will be much lower than before. So we know that they're not going to be detected with the same significance as we had hoped. But I think it's always useful to remember that this process is really fundamental to big discoveries, is to check them and to understand them and to cross-correlate them. So one thing you should check out if you haven't already is an experiment called SPIDER, spelled like spider. And SPIDER is a balloon experiment that actually launched around Christmas time in Antarctica, and they did I think it's maybe 20-day or maybe 14-day balloon excursion, and they have been making measurements of large-scale polarization. So they will directly overlap the BICEP field, and they'll also be able to give their independent data, not only an analysis, but independent data of the same field. So that's really fun. It's a beautiful launch. They put the launch on YouTube. It's really fun to watch, and the science coming out of there is going to be amazing. So keep your eyes posted.
Cool. So Lawrence Norris comes back and he says, "Oh, Cape Town is absolutely beautiful. Everyone should visit there."
Cape Town is exceptionally beautiful. It's it's hard to get any work done. It's beautiful. It's really wonderful. I was there for 3 years and I loved it. So.
Wow, I'd love to go sometime. Any other questions from our students before I ask another one? What was your trajectory into being fascinated with the cosmic microwave background? From looking at your CV, you sort of had done your master's degree in looking at dark matter, and so there's like this trajectory in fundamental questions of the universe. Has that always been sort of what your drive was?
Yeah, I mean, it's interesting. Like, some people pick a thing like stars or galaxies or whatever, and they go for that uniquely. And I've always been more interested in, I'm interested in questions that we might answer and ways we can do that with data. And that includes statistical methods. So I'm really interested in how we analyze data and how we get the most out of the data that we have. And so that means I've worked on CMB work. I've worked using exploding stars, using supernova analysis to try and get at the same problems. So I'm not actually wedded to working with the CMB, but I found it very useful to learn, first of all, learn a lot of analysis skills and also just ask particular questions of the early universe. So.
Wow. So you kind of hit on a theme. I always like to ask this question, and it's curious to see how different presenters take it. What sort of advice would you give young students who are now in their undergraduate degree preparation about going forward? What sort of things do you wish maybe you had heard when you were an undergrad? As sort of like plans for the future, or what to think about?
Yeah, absolutely. So actually, sorry?
Just said you had a great experience, so it'd be great to share.
Yeah, no, absolutely. So actually, I help run the undergraduate summer program at Princeton, and we spend time designing things in the course that we wish someone had told us when we were an undergrad. So, for example, practice giving talks. Figure out how to do that, and if you have any questions, like, you guys can email me. I have a bunch of thoughts about giving talks. Workouts, talk to someone about how to write a paper. You will soon be writing papers, and it's something that there's a skill to it, and it's very easy to get disheartened if it's the first time you've ever done something. How to talk about a paper in front of a group. So. How to read a paper and condense important information and then present it. In terms of general advice, I would say pick a problem that you think is interesting and fun, and try and ask questions. When you read a paper, try and ask questions as how they might be wrong and how you would do the analysis differently or fix something or try something new. And encourage yourself to have lots of ideas and write them down. So it's one thing that I'm still working on. I'm good at taking an idea and making it better, but what I'm trying to train myself in is having new crazy ideas. Because sometimes I'll have a crazy idea and I'll think it's crazy and that no one would ever want to work on it, and then I don't do anything, and then 3 months later someone writes a paper on the same thing. But I thought it was too crazy. So write down all the ideas that you have, and then go and speak to your professor or go and email someone or read and see if the question's been answered, and that way you really develop a sense of what you like to do and how to do it. And just as a plug, to remind you that just because you're an undergrad doesn't mean you can't do research, I put a paper out today with an undergrad student who is working with me and another colleague of mine, and don't be afraid. Like, just because you're an undergrad doesn't mean you can't ask research questions that people don't have the answer to.
That's right.
In fact, you're more likely to ask them because you're not afraid, so don't be afraid.
You hit the nail on the head. Undergrads sometimes come at problems with fresh perspectives and sometimes almost naive questions that are really good questions that you have to really think about. And we don't have a master's or PhD program here, but we do encourage our undergrads to get involved with research projects that then really forms the capstone for their undergraduate experience.
Exactly. Yeah, absolutely. Yeah. Some of the research that I still do today started from a project that I started as an undergrad.
Wow. Cool.
Because it started, and then I was like, oh, there's more interesting stuff here, and it kept going. So, yeah.
That's awesome. We've got one more question here about cosmic microwave background. Lawrence Norris asks, in the scattering processes with respect to cosmic microwave background, are photon-baron events important, or is it all photon-electron?
So I'm going to go with what I think I know, with the caveat that I might be wrong. So the dominant process is photon-electron. So it's Thomson scattering. Actually, it's kind of cool. It's the same process that's happening in the sun. So the reason why we can't see through the sun is the same reason why we can't see through the CMB. So because there are all these interactions, electron, photon, the mean free path of the photons is very small. Now, photon-baryon events, I don't think they are very important, but I could just have ignored them. But generally, it's dominated by the Thomson scattering of electrons and photons.
Okay.
But you should check.
So,
don't believe me.
So is that where that story comes from about it taking, was it a million years or so for a photon at the core of the sun to make its way to the surface, just due to that Thomson scattering and the random mean-free path?
Right. Yeah. I mean, the sun is a little bit more complicated because there are different zones, like convective zones and whatever. But yeah, right. Just because the photons are bouncing around a lot, and so they don't make it very far. It's like the awesome random walk.
Right.
And that's exactly, when the photons stop doing that in the CMB, the light just propagates towards us right. Unimpeded. So.
And that's the reason why we can't see beyond or further back in time past that time when we see the cosmic microwave background. That's basically it. Gotcha.
Exactly. Yeah. Yeah.
Okay. Cool. All right, Lucas.
You were talking about getting involved with research at the undergraduate level. Just a quick question. I know the deadline's are coming up for REUs for research experience for undergraduates in the summer. I don't know if you know of anything that's going on with any of your connections that you might want to put out a shout out for. Because,
Yeah, so we have, so it's not necessarily an REU program. It is a research program though. At Princeton, typically the way the funding works is it's encouraging Princeton students to become majors. So we have a preference for local students, but there are some students that are funded from external places. And the deadline for that, so if you Google Princeton USRP, Undergraduate Summer Research Program, there is kind of information on how to apply. Typically it's like a transcript and a little essay talking about it, and I think the closing date for those is 15th of Feb.
Fantastic. Okay, we will definitely check that out and put it on
awesome.
Our Facebook page and try to get
cool.
We are very appreciative of your time. This has been a fantastic seminar. If we have any more questions, we will let you get back to your.
Absolutely. Send me some more questions. I'm always happy.
Okay. Well, let's give our seminar speaker a round of applause.
This has been fantastic. I'm going to go ahead and stop the broadcast, and then we'll just wrap up with just a few more words, and then I'll let you go because I know you're cutting close on time.
Thank you.
All right. Thank you.
Awesome.